Hello there. In this video, I would like to talk about statistical significance. So I am going to look at some data and I'm going to conduct two hypothesis tests with different null hypotheses or different claims. So the first claim here comes from data of 785 individuals who completed 4 years of college. 144 of them are smokers, and I'm going to test the claim that less than 20% of college graduates are smokers. So for my claim, I have P is less than 0.2. The null hypothesis is always a statement of equality because it is our assumption for conducting the test. So it equals, P equals 0.2. The alternative hypothesis is always a statement of inequality. So in this case, it is actually equal to the claim that P is less than 0.2. And I am going to use an alpha or significance level, which defines unlikely in the sampling distribution, as 0.025 to correspond to a one-tailed test with that corresponds to a 95% confidence interval. Our sample statistic is p hat. And so that is our sample size of 140, a number of successes, which are the number who smoke, of 144 divided by a sample size of 785. The standard error of the sampling distribution is the square root of p 0.2. We use the p from the null hypothesis. You do not use the estimation p hat, but you're going to use the assumed value because we are assuming a distribution of sample proportions where the true proportion is 0.2 and therefore has a standard error corresponding to that 0.2. So we want the square root of 0.2 times open parenthesis 1 minus 0.2 close parenthesis divided by the sample size of 785. Now we're ready to compute the p-value. And this is a left-tailed test. So to find the p-value, I'm looking at the area in the left tail, and we're using a normal distribution. So we use norm.dist, where x is your sample statistic, comma, the mean is the value from the null hypothesis, 0.2, comma, the standard deviation is the standard error, comma, and cumulative is always true. And we get a 0.123, which is obviously bigger than 0.025. So for our decision, using our decision rule, the decision, we have p-value is greater than alpha. So we are going to not reject, do not reject the null hypothesis. All right, we do not reject. It's not the same thing completely as support. It's kind of a weak support. We can't say it's not, so we kind of support it, but it's weak. So our decision, do not reject the null hypothesis. Since we're basically supporting the null hypothesis and not the alternative hypothesis, and our claim was the alternative hypothesis, the conclusion is the sample data do not support the claim. All right, so here is a hypothesis test where the sample data do not support the claim. Well, the claim is that the true proportion is 0.2, and even though we got a sample proportion of 18%, we wanted to know, was that difference statistically significant? Meaning, is it not likely due to random sampling error? We did not support the claim, which is the statistical significance, so we support random sampling error. So the null hypothesis you could think of as claiming that the difference between the assumed parameter and the sample statistic is statistically significant. All right, so statistically significant, the difference, the difference between the population parameter, I should say assumed population parameter in H0 is significantly, in this case less than, the difference between the assumed population parameter in H0 and the sample statistic is great enough to not likely have been the result of random error. Is great enough so that the difference is not likely due to random sampling error. So the alternative hypothesis you can always think of as statistically significant. It's like the hypothesis that my sample statistic is significantly different from the value claimed in the null hypothesis. The null hypothesis, therefore, would say the difference is likely due to random sampling error. Because if we cannot reject the claim that p equals 0.2, then it means the difference was likely due to random sampling error. So the null, if you support the null, then the difference likely due to random sampling error. If you support the alternative, the difference is statistically significant. Statistically significant. Here, we did not support H1. We did not support statistical significance. Therefore, the difference is likely due to random sampling error. Okay, now I want to draw a picture so that we can kind of visualize what is happening here. So the sampling distribution of proportions is normally distributed. So this is a distribution of sample proportions. So it's a sampling distribution. It's normally distributed with the mean equal to the assumed population proportion from the null hypothesis, and that here is our 0.2, right? So this is our assumption from the null hypothesis. All right, now we got a sample statistic that was less than 0.2. We got a sample statistic here that is less than 0.2. It was about 18%. So 0.18. So we want to know then, is the difference between these two values likely due to random sampling error, which means if it's likely due to random sampling error, then that's basically saying that it's part of the middle 95% and not the bottom 2.5%. So down here you would have your bottom 2.5%, And that's where our alpha 0.025 comes from, because the bottom 2.5% is in the left tail. We want to know then, does this define a tail that is less or greater than 2.5%? And we found out, oh, the area in that tail is much greater. It's 0.123. Okay, so it actually was like moved into here, so we could see it was greater than the 2.5%. All right, so and here then is where our p hat would be. I'm sorry, here then marks off the tail, where this tail is greater than 2.5%. All right, so that's when we saw that, oh, it's within the likely values due to random sampling error, so it's not statistically significant. Now, there's always a chance you make a mistake in your hypothesis test, right? Nothing is certain in probability or in statistics. So it is possible that by not rejecting the null hypothesis, that we actually might have supported a false statement and made an error. So when you do not reject the null hypothesis, okay, if you do not reject the null hypothesis, then the possible type of error is accepting the null hypothesis when it's actually not true, and that's what we call a type 2 error. So here we have a possible type 2 error, which is, let's put it this way, not rejecting the null hypothesis when it is false. Okay, so a possible type 2 error here because we did not reject the null hypothesis, because we got a sample statistic that would be in the middle 95% of a sampling distribution with a mean equal to 0.2 and a standard error of 0.01427. All right, so not statistically significant here. All right, not statistically significant. Now let's look at an example that is statistically significant. We saw that this difference of, a little less than 0.2, not statistically significant. So what if we made the difference between our p hat and our assumed value in the null hypothesis a little bit larger? So let's now conduct this test with the claim that the population proportion is less than 0.22. So let me just kind of put that in here. We're going to change it now to less than 0.22. So now each of these has to become 0.22. Well, our p-hat's not going to change because that had nothing to do with the 0.22, but our standard error will change because now we need to compute the standard error under the assumption that the population parameter is 0.22. So middle of the curve is 0.22. Okay, now we go to here, okay, I have to now change my assumed mean to 0.22. The other values, the p-hat and the standard error, automatically changed because I had clicked on these cells. So the only thing I have to physically change is the 0.22. So I make that little change, and look at this now. Now we have a really small p-value. Before we had a large p-value. Now we have a very small p-value. So the decision here, because our p-value is now less than alpha, we reject the null hypothesis which means we are supporting the alternative. We are supporting statistical significance. So the sample data support the claim. So now the sample data do support the claim because we rejected H0, we rejected the assumption and supported the alternative, which is the claim. So the difference is not likely due to random sampling error here, but the difference is statistically significant. The difference is statistically significant. All right, so this time the difference between these two is statistically significant, not likely due to random sampling error. So we're gonna have a different possible type of error for this one. But let's look at a picture for this. What does this one look like? Well, still the same basic picture. It's the only thing that really changed was our assumption, but then that resulted in a big change in the p-value. So we still have the assumption that I'm sorry, not still, but now we have the assumption that p equals 0.22. We have a p hat of 0.183, and so we want the area in this left tail, and now we got this really small area because that's this value here, the 0.006. That is now this red area. So the middle 95% is over here, right? So here's the middle 95%. So we can see then the difference was beyond the likely values that would be due to random sampling error. It is unlikely to be due to random sampling error. This is the probability basically that getting this value or something more extreme as in further away, the whole tail, okay, that probability is only 0.0067. So the probability of getting this value under this assumption is really small. Like, well, that's a really small probability. All right. Well, since the probability is so small, it's more likely then, right? Looking at the probabilities, it's more likely then that our null hypothesis was wrong, and so that's why we reject it. And so if our null hypothesis is wrong, then we support the claim and get our statistical significance, right? Now here, the possible type of error we could have made is rejecting this null hypothesis when it was actually true, right? Because we look at this and we're like, yeah, that value is in the range of possibility, but it's definitely far from probable. It's very improbable, all right? But it still exists that we may have committed what we now call a type 1 error. So I should say this is a possible type 1 error here. And a type 1 error is rejecting the null hypothesis when it's actually true. So rejecting the null hypothesis when it is actually true. Now, of course, we don't know if we've made this error or not, but we know the probability of making this error because we are going to make this error if we end up with something way down here in the left tail. right? If anything that moves beyond the middle 95%, anything beyond that would be considered unlikely, and therefore we would reject the null hypothesis, right? So in this picture here, this distance here, that's the 2.5%. That is alpha, okay? That's alpha right here, right? We got a value less than alpha, okay? So the probability that we made a type 1 error is alpha, because that's the probability that we are going to reject a value that actually occurred when the assumption was true. So the probability of a type 1 error, so the probability of a type 1 error is always equal to the alpha you select. And that's why we want to make sure that our alphas are small enough that we don't commit this error, because we consider this to be the worst error, rejecting something when it's true. We consider that to be a more serious error than type 2. So we want something that's small enough to decrease the chances of making a type 1 error. Okay, we want to decrease our chances of claiming statistical significance when there was really random sampling error. Okay, looks statistically significant, but it was actually due to random sampling error, okay, type 1 error. So we want a small alpha, but you don't want something so small that it's just impossible to attain according to your methods. So most of these we'd use like 0.025. Some, if you got a big sample size and a really important null hypothesis, you might want to go to 0.01 or even 0.001. So statistical significance is when the value in the null hypothesis, your assumed value, and the statistical, or I should say the sample statistic, the difference between the assumed value and the computed sample statistic is said to be statistically significant if the difference between them falls beyond the middle 95% here, in this case of 0.025, or I can say if the difference here is smaller or than the 0.025, so it's basically in the tiny left tail, it's in that tiny left tail, so that's where we go, oh, unlikely, reject the null, support the alternative, statistical significance. But it's possible that it's still wrong. It's just not probable. And the possibility that we're wrong is the probability, all right, that we've decided will be unlikely and that we'll reject it. So probability of a type 1 error. The probability of rejecting the null hypothesis when it's actually true is alpha. So your probability of thinking or claiming, let's say the probability of having statistically significant data, yet it be actually due to random sampling error, is alpha. All right, thank you for watching.